Okay, in this lecture we're going to be talking about the structure of the atmosphere. So some questions for you. What do you think the function is of the atmosphere? Why do we need an atmosphere? Think about other planets like Mars and Mercury that don't have atmospheres or have very thin atmospheres, and think about what does our atmosphere provide for us? What is the composition of our atmosphere? What do you think the atmosphere is made out of? What could be the most abundant gas in our atmosphere? Let's talk about it. Alright, so the function of the atmosphere is to allow life to exist on Earth. Life on Earth could not exist if we didn't have an atmosphere. It allows life to exist by regulating temperature, making sure it's not too hot or not too cold. It provides protection from harmful solar radiation. So while we do need the sun's heat in order to sustain life, too much of it is dangerous. It provides a space for water and nutrient cycles to exist, and we're going to talk more about a few of those cycles later in this unit. What the atmosphere is actually made out of is 98% nitrogen. The most abundant gas in the atmosphere is not oxygen. Oxygen is actually very, very flammable. Pure oxygen is very flammable. So if our atmosphere were too much oxygen, it would actually be flammable. So the most abundant gas in our atmosphere is nitrogen, followed by oxygen, and then the rest of it is a mixture of water vapor, carbon dioxide, argon, helium, hydrogen, ozone, particles like dust and soot, and chlorofluorocarbons, and a whole bunch of other things. But most importantly, 78% nitrogen, 21% oxygen. And you can see a pie graph here breaking down the composition of Earth's atmosphere. The most important of these other gases for weather is carbon dioxide, simply because of the molecular structure of carbon dioxide. Let's take a look. This is a carbon molecule, and because of the way that carbon bonds together, it actually is responsible for holding in a lot of the sun's heat, which in moderation is perfect for sustaining life on Earth. We need heat in order for plants to grow, and plants are the food source for all life. So what carbon does is it reacts to heat incoming from the sun by creating this kinetic energy, as you can see from these molecules bouncing. Those molecules bounce, they actually create more kinetic energy. So they absorb the sun's heat, they help to radiate it back down to the Earth, and they also create more energy through their kinetic energy. And in moderation, this is vitally important to sustain life on Earth. So carbon dioxide and water vapor play a critical role in regulating the amount of heat energy that the atmosphere absorbs. So we need carbon in our atmosphere and water vapor as well in order to absorb a sufficient amount of the sun's heat and maintain that heat inside of our atmosphere in order to support life. Alright, so the structure of the atmosphere, starting at the bottom, which would be starting at sea level, or where we live. The first layer is known as the troposphere, then the stratosphere, mesosphere, thermosphere, exosphere. And a way to remember this is the sun makes thermal energy. So another way to remember mesosphere, this prefix meso, this means middle. So the mesosphere is in the middle. And exo, this prefix exo, this means outer, like an exoskeleton is a skeleton that's on the outside of an animal or an organism, so the exosphere is on the outside. And this is an image showing the different layers and the auroras, which happen in the thermosphere. Some satellites are orbiting in the exosphere. So some characteristics of the troposphere where we live. So this is one of the layers of the atmosphere that is most vitally important to us. It contains most of the atmospheric mass, and it's where weather occurs. So when you hear the term weather, it only occurs in the troposphere. Pollution and smog can easily collect in the troposphere, and temperatures decrease as altitude increases. And that should be common sense, because when you climb a mountain, the temperature drops. So it's much warmer at sea level than it is at the top of Mount Everest. The reason for this is the amount of heat-absorbing molecules, so that carbon dioxide and water that I was talking about, decrease as the distance from Earth's sun increases. So at the top of Mount Everest, I'm sure you've heard of climbers that have trouble breathing because there's not a lot of oxygen molecules. This is also what causes the temperature to decrease. There's not as many molecules to absorb the heat. It is the layer closest to the Earth's surface, so the bottom boundary is sea level and the top boundary is about 10 kilometers, but that does vary from the equator to the poles. And here's a picture of weather occurring in the troposphere. Our next layer is the stratosphere. And it contains ozone gas, which makes the ozone layer, which helps to deflect some of the harmful UV rays from the sun, which helps to prevent us from getting skin cancer. Jet planes fly in the stratosphere because of steady weather conditions. So as I said, weather really occurs in the troposphere more than any other layer in the atmosphere. So in order to avoid all of the weather that occurs in the troposphere, jet planes tend to fly in the stratosphere. Temperatures increase as altitude increases. So this is the opposite of the troposphere. In the troposphere, as elevation increases, temperature decreases. It is the opposite in the stratosphere. As elevation increases, so does temperature. And this has to do in part because of the ozone layer at the top is absorbing a lot of the heat from the sun. So the bottom boundary starts where the troposphere stops at 10 kilometers. It goes up to about 50 kilometers, so it's about 40 kilometers thick. We have all this wonderful protection from the ultraviolet radiation, the UV radiation from the sun. All right. Our next layer is the mesosphere. Air molecules in the mesosphere are less concentrated than they are in the stratosphere. So what this does is it causes the temperature to decrease as altitude increases. So the opposite of the stratosphere, simply because there are fewer air molecules. With the absence of ozone, the temperature again decreases as the number of heat-absorbing molecules decreases. Again, it starts where the stratosphere ends, and it goes all the way to 100 kilometers, which makes it about 50 kilometers thick, which makes it about the thickest, it is the thickest layer of our atmosphere. So here's a nice graph demonstrating the correlation between temperature and elevation in our atmosphere. So in the troposphere, as the elevation increases, the temperature decreases. It is the opposite for the stratosphere. And then the mesosphere, it's the opposite again. As elevation's increasing, the temperature is decreasing. And then you can see what's happening in the thermosphere. Again, as the elevation is increasing, the temperature is increasing because it's getting much closer to the sun. So as I mentioned, most jet planes fly in the stratosphere, so in this layer of the atmosphere. And if you look here, the temperature in the stratosphere is about negative 60 Celsius. So if you've ever flown in a jet plane and you look at the window, you'll sometimes see ice crystals forming on the outside of the window, and that's because it's negative 60 outside of that airplane. So the next time you fly in an airplane, be not only grateful for pressurized air, but also for heat. And the thermosphere. Gas molecules are very sparse and widely spaced in this layer of the atmosphere, so temperature increases as the altitude is increasing. Also because you're moving closer to the sun. This layer of the atmosphere is closer to the sun. So the molecules are heated faster because they're close to the sun and they are absorbing a lot of intense solar radiation. Temperatures are very high, up to 1,000 degrees Celsius in this layer. Again, it begins where the mesosphere ends, and the top boundary is 100 kilometers. So the approximate thickness is 40 kilometers. So I said earlier the mesosphere is the thickest. It's the thermosphere that is the thickest layer of our atmosphere. Alright, and then we have the ionosphere, which is really not its own layer of the atmosphere. It is incorporated into the thermosphere. It is made of electrically charged particles that are known as ions. At the poles, ions interact with air molecules to form what are known as the auroras or the northern lights. And radio waves from Earth reflect off of the ionosphere back to Earth. So the next time you listen to the radio, you can think the ionosphere. And here's an image of those beautiful northern lights known as the auroras. So some characteristics of the exosphere, which is the outermost layer of our atmosphere. The air molecules are very sparse in this layer, and only light gases like helium and hydrogen can be found. So the temperature is definitely increasing as the altitude is increasing. Temperatures are high. And it really doesn't have a top boundary because it's kind of fuzzy, really distinguishing where our atmosphere ends and where space begins. And here it is, looking down on our beautiful planet through the exosphere. Okay, so this is just a summary of the characteristics of our atmosphere. So again, the correlation of temperature to altitude, different types of radiation that are actually able to be absorbed and reflected by the different layers. And here's the ionosphere, which is reflecting the radio waves and where the auroras happen. Really is fascinating. Okay, so some final questions. What are the layers of the atmosphere? Make sure you know those, review those. And I also want you to create a graph of the layers of the atmosphere that demonstrate the variation in temperature. So recreate that graph that shows correlation between temperature and elevation. You are going to be expected to know that because it's a very important characteristic of our atmosphere. And that's it.